So the next thing we want to do, having looked at this sort of impact of relativity, is we're now going to do in the Newtonian way the derivation of the equations which are going to govern the evolution of the universe. And the first one of those, the most famous of those, is what's called the Friedman Equation. And it's going to describe, or give you the route to getting the scale factor as a function of cosmic time. So, how do we go about setting this up? Well, it's kind of remarkably simple in a sense. So if we imagine that we have some spherical area here with a density inside it where rho is a constant, and it is freely expanding or contracting, and we'll consider some point mass here m. Oops, didn't really work. Let's try that again. Some point mass here m, some distance here r from the centre. And this doesn't necessarily need to be the edge of the universe. So you might, for example, just have this being some point in the universe, and there's universe inside and outside you. But a neat thing about gravity and 1 over r squared laws in general is that you don't see the material which is outside you in terms of its gravitational effect. So for example, if I were to go down into the earth, right, in the middle of the earth, you're weightless because all the different mass outside you all cancels out. And so what you care about is what is interior to you. So if I go down through the earth, the gravity gets weaker and weaker and weaker because I don't care about the material which is outside me. So it's not that I'm here drawing the edge of the universe, I'm just drawing some point in a freely expanding or contracting universe. And what I can write here is that the force on that test mass, F, is just minus gmm over r squared, where capital M here is the mass interior to the test mass. Test mass has mass m, obviously r squared. Now, that mass interior, we want to express rather than being the mass, right? What's the mass of the universe is a complicated thing. What's the density of the universe, especially if it's isotropic and homogeneous and the same everywhere, is easier. So the mass m is just equal to the volume, 4/3 pi r cubed, times the density rho. So the force can then also be written as minus 4 pi g rho m r over 3, just substituting in for mass here. We could also write down the gravitational potential energy. And so in that case, V equals minus g mm over r, which is the same as the force, except you've got one less factor of r on the bottom, so one more on the top when you multiply, gm r squared over 3. And you can look at the kinetic energy. Call that T. That, of course, is a half mv squared, but the only velocity here is the velocity of the expansion, r dot, dr by dt, so r dot squared. And since total energy is conserved, we can just add those together. So the total energy U is just the potential plus the kinetic, which is equal to 1/2 mr dot squared minus 4 pi g rho mr squared over 3. And this still contains a kind of awkwardness because it's got a physical distance in it. It's got an r. And that's actually quite tricky. We're not quite sure what to do with that because distances are kind of awkward. And so what we're going to do is we're going to make a switch to something called comoving coordinates. And so if, for example, I have a set of coordinates here, and here I have x equals 1, 2, 3, 4, and then they're in an expanding universe, so the universe expands, my choice is that I'm still going to have x equals 1, 2, 3, 4, even though actually my physical distance has increased. So my r as a function of t is going to equal a as a function of t times x. And a here is, of course, the scale factor, and x is essentially the scale, the fixed thing. And so this is a switch to co-moving coordinates. So x is always 1, 2, 3 or 4. It co-moves. And so if I substitute that above, remember x doesn't change, so when I differentiate x, 0, dx by dt equals 0. Remember x dot equals 0, so therefore when you have to do both of the differentials in the kinetic energy, one of them is going to vanish. And then you get the total energy is just 1/2 ma dot squared x squared, and the other term of course is 0, minus 4 pi over 3 g rho a squared x squared m. And now I'm going to multiply both sides by 2 over ma squared x squared, i.e. basically this bit here. And that gives me a dot over a squared equals 8 pi g rho over 3 plus 2u over m x squared a squared. And this actually is quite interesting already. You can see this. It's going to link something about the expansion because this here, remember, is the Hubble parameter squared. It's going to link, not very well written. It's going to link something about the expansion because this is the Hubble parameter squared with something here about the density, with something here about the total energy. And quite commonly, we will replace kc squared equals minus 2u over mx squared. And then that gives us the normal version of what we call the Newtonian Friedman equation. Which is a dot over a all squared equals 8 pi g rho over 3 minus kc squared over a squared, and of course that is all equal to h squared. And k here is the curvature. So the total amount of mass energy that you have in the universe dictates whether or not the universe is curved. There is also, and this is what we will use because it's what you tend to see used, a relativistic version of the Freedman equation. And that looks like the following. And there's a few crucial differences that are made here. So the first, box that's very important as well. The first difference is you've changed rho to E over C squared, i.e. E equals rho C squared, and this is the energy density. And this is the matter density. And that's simply to allow for the fact that photons have energy density. So, i.e., from special relativity, we know that E squared equals m squared c to the 4 plus p squared c squared. So radiation, i.e. photons, can alter the evolution of the universe. Second change is we've changed K at the top here to kappa, or I'll actually leave it as K because I can't really write kappa very clearly, and we've then subsequently rescaled with R0 squared. So rather than writing KC squared over A squared, I now get K kappa C squared or KC squared over R0 squared A squared. And so the kappa, or the K to kappa, what that does is it normalizes the curvature by the radius, and therefore get essentially limited ranges for K. More on that in a minute. And they're really the main changes that you see occasionally. You'll see something like plus lambda over 3. And this is something we will come on to talk about a lot as well, which is called the cosmological constant. But for how we're going to deal with that, we'll always roll that into the energy density. So there you have it. This here, it was suggested when I learnt cosmology I should write this backwards on my forehead, so I saw it in the mirror every morning and learnt it. You don't need to do that because it will of course be given in an exam should you need it. But it is one of the core experiments, the core equations in cosmology, because it allows you to link something about the expansion with the energy density, how that evolves, and the curvature. On the other hand, it has too many unknowns because I don't know what the scale factor is doing, I don't know what the energy density is doing, I don't know what the curvature is doing. So I can't yet solve it, I need some more things to solve it, but I can look at some of the implications that just this equation has for the evolution of the universe. And we'll do that in a minute.